We're getting ready to start talking about one of the most common applications of integration, which is how to calculate volumes of some solid figures. And we'll get into that further soon, but this video is dedicated to some skills that you're going to need in order to do that process. So let's start with just looking at a graph. This is e to the x plus 1, just an exponential curve. And this green spot, xy, this is just going to represent a generic point along this graph. Now I could have put this green spot anywhere. Alright, so one of the main ideas here is we're talking about a generic point. So these distances that we're getting ready to write, they apply no matter where this point is. And that's important because the point is going to move across the graph as we integrate. And so the skill that you need to have is you need to be able to come up with how long this blue line is. Now, if the green spot is able to move, obviously this line doesn't have just one distance. I can't just say, oh, it's 3.1, because I could have put the green dot anywhere. So I need an expression or a function for the length of this blue arrow. Now, here's a fact. The distance from the x-axis to a generic point xy is y. The vertical distance from the axis to a graph is called y. That's what it means to be on this two-dimensional Cartesian coordinate system. We call the height y. And since this function happens to be y equals e to the x plus 1, the other option for naming the length of this blue arrow is e to the x plus 1. Okay? And I don't know if that seems obvious, like of course that's how long that line is, or if you're thinking, well, why does that matter? Don't worry about why right now, just worry about those are the two ways we could name that length. So then how about this little purple arrow? How long is that purple arrow? Well, no matter where this green point goes, we could call it x. All right, the distance from the y-axis to a graph is called x. And the other distance, let's say I needed to express that distance in terms of y, for reasons we'll learn shortly. The x is what I would get if I solve this equation for x. So I would subtract 1, and then the opposite of e is natural log. So x is the same as natural log of y minus 1. So that's another option. If I need to name the distance, how long that purple arrow is, I can either call it x or I could call it natural log of y minus 1. So the big fact from this screen is the horizontal distance from the y-axis to a graph is called x, or whatever the function is solved for x. The vertical distance is either called y or the function, the x part of the function, this side of the function, which is the same thing as y because that's the equation we're looking at. Okay, so take a minute and see if you can find two names for each one of these distances. Okay, I'm going to encourage you to pause and write these, fill out 1, 2 in orange and 1, 2 in blue. See if you can find those. And then resume and see if you got them. So remember that this blue line right here, its distance, its length, has two names. One of them is in terms of x and one of them is in terms of y. And this is the graph of y equals sine x that we're looking at. So one option is always just to call it y. The distance from the x-axis to a graph is always called y. And that's true whether I put the point where it is or put the point here or here. The vertical distance is always y. Even if it were over here on the negative side, the vertical distance is y. The other option for naming that point is sine of x. Right, because y equals sine of x. So we're not finding anything different in our option 1 and option 2, we're just finding another name for it. And up here in orange, one option is going to be x, because the distance from the y-axis to the graph is always, one option for that is always x, and the other one is what does x equal? And x is equal to sine inverse of y, if we were to take our equation of our graph and solve it for x. That would involve inverse sine of both sides. So that's my two options for each one of those distances. Alright, so let's mix that up a little bit. What if we need the distance from a point on the graph? So here is our point xy that is on the graph of the parabola y equals x squared. Remember, this is generic. All right, it's not a special point. This could be anywhere on this graph. So how far is it from that point all the way down to the line y equals -1? All right, how long is this green segment that we're looking at? Okay, so there's two options. Remember that the vertical distance from a point to the axis, that's called y. On our previous two screens, we've been moving from the axis, but this distance goes all the way down. But that's not a big issue. We're just going to add 1 to it. So one name for this is y plus 1. And since y equals x squared, the other name for it is x squared plus 1. Okay, so all we did was take this 1 unit right here and add it on to values that we would have found before. So that entire green segment is y plus 1. Okay, and then moving sideways, remember this portion of the distance right here, if we're looking for the length of this purple segment, that much of it right there has two names. They are either x or, in this case, the square root of y, because if we solve our function for x, we get the square root of y. So just that much of it is x. But remember, we also have this part over here, because we're not looking at the distance to the y-axis. We're looking at the distance over here to x equals -2. All right, so if you put those two things together in purple, if you have this x and this 2, we have x plus 2. That's one option, because the horizontal distance from the axis to the graph is x, and we are extending that by 2. And that 2 is constant no matter where you go. If I were to make my point way up here somewhere, this would be x, and this would be 2. Now that x plus 2 was longer than this earlier x plus 2, but that's just because we're on a different piece of the graph. All right, we've got a variable section that grows or shrinks as we move up or down, and we've got a constant portion of 2. Okay, but either way, that x plus 2, remember that x is the square root of y. So that distance, that purple distance down here, both of those names could describe that purple distance. All right, so here's a little bit of variety. Let's come up with some names for these distances. So we have the graph of the square root of x and the graph of y equals 1. Let's just do one name for that purple distance. So let's use some facts that we've learned. That purple distance would be, let me get some more colors involved here. That purple distance would be this distance, this red line I'm adding, which is 4. No matter where I go, the distance from that purple dashed line to the x-axis, which is down here, is 4 units, because that's the line y equals 4. So if my goal is how long's the purple one, let's add in another. Let's add an orange. The distance from the axis to the graph, no matter where I go along that graph, has some names that we've talked about. Let's do this one in terms of x only. That distance it has two names. It's either y or the square root of x. So if I want the purple, would you agree that that purple is the total length 4 minus the square root of x? We could call it 4 minus y, but I'm just going to do one option. So that one option is 4 minus the square root of x. All right, because we're just using some simple geometry, some segment addition or subtraction. The long arrow 4 minus the orange arrow square root of x gives me the purple, which is 4 minus the square root of x. Okay, this blue one is a consistent 3 no matter what. This thing has one name, and that's 3, because it goes from the line y equals 1 to the line y equals 4, so that's going to be a consistent 3 no matter what. And let's talk about the green one. The green one is a difference in a couple distances also. So that green spot, use blue here, the distance from the x-axis up to a graph, as we've learned, is always called y, or in this case it could be called the square root of x. This distance right here is 1 no matter what. So that green distance is the square root of x minus 1. Because the square root of x would have been the full blue arrow, but we're taking 1 off of it because our green rectangle doesn't extend all the way down to the axis. It's 1 shorter than that. So on the previous screen we added to those distances that we had found because our distance was defined by going beyond the axis, down below it, or over to the left of the y-axis. Now we are making our distance actually shorter by not going all the way to the axis. We are going only down to the line y equals 1. So that is 1 unit shorter than the graph would have been without it. And finally, remember that any of these distances can be expressed in terms of x or in terms of y. So if y equals the square root of x, as it does because that's the function we're looking at, we could also call that green rectangle y minus 1. Because y is the full distance shown here in blue, 1 is the purple distance here, so another option would be y minus 1. For certain volumes we'll use the y version, and for certain we'll use the x version. That's what we have yet to learn. Okay, so I know those pictures got a little crowded and hectic, but being able to name these distances is the very crucial first step to being able to calculate volumes.